And that brings us to the one of the most important things we're going to talk about here early in this semester, something that we're going to lay the foundation for the remainder of your organic chemistry learning, which is how do we use curved arrows to describe reactions. So we're going to use the same curved arrows, very similar to what we did for resonance. But now what we're actually going to do is we're going to show how the electrons change from the reactants to the products. Like for example, in this acid-base reaction, we draw these curved arrows starting from the lone pair on the base, pointing to the proton in the acid. That indicates that this lone pair on the base is going to form a bond between the base and the proton. At the same time, this proton A bond here, this is the conjugate base here, we're showing that starting from this bond, that is pointing at the A atom here, what happens is this bond breaks. And we already knew that. We know that this proton is going to be transferred from the acid to the base. As part of that, this hydrogen A bond has to be broken, and that leaves us with a lone pair on A. So now we're actually showing the physical flow of electrons from the reactants to the products. As I mentioned, this is one of the most important skills in this class. That's why actually this lecture is going to be relatively short. There's going to be a lot of practice at the end of this, so you can work on that. So now, like if we're looking at a specific acid-base example, so here what we have is we have a hydroxide ion with acetic acid. So imagine titrating acetic acid with sodium hydroxide or something like that. Well, what happens is the hydroxide, as you know, reacts with the acid, picks up the proton and becomes water, so that becomes the conjugate acid. And then we're left with the conjugate base in this case, which is acetate. As we draw the curved arrows here, the first thing that happens is that the lone pair on the base attacks the proton on the acid. Again, the way that we're showing this is the curved arrow starts from the lone pair on the base and it points at the proton. That indicates we're forming a new oxygen-hydrogen bond. So because it starts from a lone pair and points at a new atom, that says, hey, there's a new bond forming here. So it's going to be a new OH bond. Then looking at acetic acid, we're going to break the OH bond in acetic acid. So we draw the curved arrow pointing at this OH bond. It points to the O. So that tells us that this shared pair of electrons is going to become a lone pair of electrons on this oxygen here. And that's exactly what we see on the conjugate base here. Now, these have to happen simultaneously. So we draw both arrows in the same time. It's what we call a concerted mechanism. Both steps happen at the same time. Now, here's just one example of a multi-step mechanism that you can see. And this is going to be kind of a simple example of something that we'll see later on. This is an elimination reaction. We'll cover that in chapter 7. So as we follow through, let's just follow through and see what kind of reaction we have at each of these steps. So first we have T-butanol. So this is T-butyl alcohol from our previous example. The lone pair on the oxygen is going to form an OH bond, a new OH bond, with one of the hydrogens from a hydronium ion. At the same time, when this new OH bond forms, the OH bond in hydronium has to break. So this OH bond becomes it becomes a lone pair on the hydronium ion, on the oxygen in the hydronium ion, which then is, of course, water. So this is one step. We also want to point out there's a proton being transferred from hydronium to T-butyl alcohol. This is a pretty good example of a proton transfer reaction. Next up, what we have is we have this step, which we haven't covered yet, but we're going to cover these patterns in the future. But what we're showing here is we have a carbon-oxygen bond. This carbon-oxygen bond is going to break. So we point the arrow from this carbon-oxygen bond, and it's pointing at the oxygen. So it stops being a carbon-oxygen shared pair or covalent electrons, and now it's going to be a lone pair on the oxygen, forming water. So that leaves us, so we lose water. This is a simple way of writing, oh, we're getting rid of water. We're not worried about the water. In organic chemistry, we're focusing on the organic chemical. And that leaves us with this carbocation. Now, this carbocation, it can be subject to an elimination reaction. Again, this is something that we'll talk about in the future. For now, we're just kind of like following through the different types of electron transfers that can occur. So here what can happen is this water can act as a base. It can form a new OH bond, so it's going to pick up this proton and abstract that proton in a proton transfer. At the same time, this carbon-hydrogen bond is going to break. And when it does, now we're not pointing at the carbon here, we're actually pointing at another bond. So this is a carbon-carbon sigma bond. When we start from a sigma bond like this and we point at another bond, that actually indicates that we're forming a pi bond. We're increasing the order of the bond. So this goes from being a carbon-carbon sigma bond to now all of a sudden it's a sigma and a pi bond. So it's a carbon-carbon double bond, just like that. For now, again, we're just doing proton transfers, so don't worry about like how does an elimination work. Don't worry about that. We'll get there, I promise. Okay, and so now is the time. Why don't you go ahead and try to draw the curved arrow mechanism for each of the following acid-base reactions. This is sample exercise number 2. Again, this is going to be in a separate video where I'll walk you through each of the sample exercises, but give it a shot for now, and we will pick up our lecture from here.